Today we're going to be talking about another side of applied trigonometry that we use a great deal, especially in physics. This is going to be all about vectors. Our goals today are to find the magnitude of a vector, that's how long or the number that you can assign to a vector, to write a vector in component form that's broken up into its x and y in two-dimension or x, y, and z direction components. Our goals to continue to sketch a vector and to find the sum and scalar product of vectors. Let's talk about some vocabulary before we go forward. First of all, the magnitude is the length, and length is in quotations there because vectors can be used to express length, but they can also be used to express any quantity that has some kind of a direction. So magnitude is the length of a vector. A vector is a quantity that has both a direction and some kind of value or magnitude. And a component, or a part, usually are horizontal and vertical. So a component's a part of a vector that we can use to represent it. So we might talk about a vector in terms of its x and y direction. To see this a little bit more clearly, let's take a look at what a vector might look like. So remember that vectors have direction and magnitude. Examples of vectors that we might use on a regular basis could be for velocity, when we might say something like 30 miles an hour northwest or northeast. We might say 3 newtons at 45 degrees above the horizontal as a force vector, or we might describe a vector as 3 units right and 2 units down as far as a movement. We can notate vectors in a variety of different ways. The first is the same way we describe a ray. If we look at the vector I have here, this is vector PQ or vector V. Vectors are usually indicated in a textbook by using a bold font. They're also sometimes written with these pointy brackets. In fact, every time you write a vector as its components, you're going to use those pointy brackets. Depending on the field, sometimes vectors are also notated as something like this, which we call an I hat or a J hat. And any of these are things that you might see when you're talking about vectors or you're reading a different textbook, whether it's in engineering or in physics or in math about vectors. Let's start with the magnitude of a vector. To find the magnitude of a vector, we tend to write that with double bars surrounding a vector name. We're trying to find the length of the ray representing the vector. And if I set this up, I have my vector PQ. The magnitude of vector PQ is the length of this ray. You might recognize that we can set this up into an x, y, and PQ sided right triangle and use the Pythagorean theorem to solve this by plugging in x squared, y squared, and solving for PQ from PQ squared. And this is going to look exactly like the distance formula, which it is. Let's talk about the component form of a vector. Instead of saying that something is moving at some speed at a specific angle, we could instead say that it's moving at a certain speed in the x direction and a certain speed in the y direction together. So instead of writing a vector as an angle and a magnitude, sometimes, and pretty often actually, we write a vector as its x and y components, x comma y, and again those pointy brackets are what we're going to use to denote that we're talking about a vector instead of a coordinate. So that a vector from the point 2 comma 3 to the point negative 4 comma 5 could be written in component form as negative 4 minus 2 comma 5 minus 3 or negative 6 comma 2. As an example, If we're trying to find the component form and magnitude of vector v with initial point 4, 7 and terminal point, that means the end of negative 1, 5. So our vector is going to be going in this direction. We're trying to find so the components for this and the magnitude for this. Let's start by taking the initial point and subtracting the final point from that. So if we're going from 4 to negative 1, we're going to do negative 1 minus 4, end point minus initial point. And if we're going from negative 7 to 5, 5 end point minus negative 7. I'm okay.
Hi. How are you?
I'm okay. How are you?
I'm fine.
Why do you use this room as your locker? You have a locker.
Yes, I do.
Why don't you use your locker?
Because we legal stuff here.
Yeah. You have a locker. Why don't you use your locker?
I use it.
Okay. Go on. Come on.
What else do I need?
Go quick. I'm recording.
Oh, sorry.
To finish this out, negative 1 minus 4 gives me a negative 5. 5 minus negative 7 is going to give me 12. So my components are negative 5 in the x direction, 12 in the y direction. To find the magnitude of this vector, I need to take these components and turn them in to a Pythagorean type thing. So if I have negative 5 in the x direction and I have 12 in the y direction, I can set this up as the square root of negative 5. That's the difference of these two again, squared, plus 12 squared. And you might see that the magnitude of vector v is going to come out as 13 because we have 5 squared, 25, 12 squared, 144, sum is 169, and the positive square root of 169 is going to be 13. Let's spend a minute talking about some vector operations. To start with scalar multiplication. You may remember when we talked about matrices earlier in the year, or during your Algebra 2 class, that scalar multiplication is just multiplying by a number. And if I look here, if I start with the vector v, if I multiply it by the scalar 2, it's going to produce a vector twice as long, but in the same direction as v. If I multiply it by half, it's going to produce a vector of half the magnitude, but in the same direction of v. If I multiply it by a negative 1, I get a vector of the same magnitude, but in exactly the opposite direction of v. If we think about this geometrically, scalar multiplication by a number, let's call that number k, is just a vector in the same direction, but k times as long in terms of magnitude. A negative k is going to flip the direction and be in the exact opposite x and y directions. We can also add two vectors together. You might think about this if you walk in one direction for some time and then change your direction and walk in a different direction. You could represent that either as the sum of your two vectors that you walked, or a vector starting from where you began and ending where you ended up. If we take a look at the two vectors that I have here, u and v, and I put them together, we end up with going v and then u. And if we think about adding them together graphically, the sum is something called head to tail, where I take the head of one vector and connect it to the tail of the next one. So v plus u can be represented that way. The sum is going to have the same initial point and the terminal point of whatever the last vector is. So the resultant vector, that's what we call the sum of two vectors. U plus v is going to be have its initial point at the beginning of v and have its terminal point with the vector u. Algebraically, we just add the components together. Let's take a look at how that might happen. If I have two vectors, vector v equals negative 2, 5, and vector w equals 3, 4, let's try to find 2 times vector v, the vector w minus v, and the vector v plus 2w. First off, let's start with 2 times vector v. If v equals negative 2, 5, twice v is going to be 2 times negative 2. So we have negative 4 in the x direction, 2 times 5, 10 in the y direction. If we have w minus v, all I'm doing is taking my components and subtracting them. So 3 minus negative 2, x minus x, and 4 minus 5, y minus y, which is going to lead me to 5, negative 1. If I'm finding the sum, v plus 2 times v plus 2 times w, what I'm going to have is negative 2 plus 2 times the x component of w, which is going to be 6, the y component of v, 5, plus 2 times the y component of w, 8. My result will be 4, 13.